Yeah. So in the last lecture, we were discussing the winner takes all learning rule. Okay. And what is the weight update equation for winner takes all learning rule? First of all, it is supervised or unsupervised? Winner takes all.
Unsupervised. It was supervised.
Unsupervised. Do you require any labels associated with the data? In this case, it's a clustering. It's used for clustering, right? So it is unsupervised. Okay, it is unsupervised, and this is a learning rule which works on a layer of neurons, rather than a single neuron. Okay, you require a layer of neurons. That layer represents the clusters. Okay, that means the number of neurons in the layer represent, okay, the number of clusters. Okay, and how do we proceed with the algorithm? What is the first step? You find out the winner, right? You find out from this layer which is the winner, right? And what is the contention? Or how do you decide who is the winner? On the basis of either the inner product, right, or the Euclidean distance with the pattern. So for a particular weight vector which is connecting to a neuron, you check whether that particular, so these are my inputs. This is one neuron. There are n number of neurons here, right? So it is connected completely, right? So suppose, so what you're doing is you're presenting the first pattern. You are finding out of these three neurons, which of the neurons it is influencing more, right? So which weight vector is actually closer to this pattern which is presented right now. Okay? So accordingly, you use either of these two measures, either the inner product or the Euclidean distance. Higher the inner product, higher the weight vector is influenced by the pattern, right? That means it is closer to the pattern. Okay? Higher the inner product, it is close, indicates that the weight vector is closer to that pattern. So if you are using inner product as the measure for deciding the winner, then you will choose the neuron with the highest inner product as the winner. Okay? And in the case of Euclidean distance, what do you do? Of course, it is a distance measure. So whichever weight vector is having the least distance with the given input pattern, the least distance with the given input pattern is the winner. That means it is closer to that pattern. Okay? And you update, after you decide the winner, you update the weights of only the winner. So weight update is only for the winner, right? And what is the weight update equation? Some learning constant times x minus that weight, right? So this is how you updated the weights, and this is winner takes all learning. Okay. So today what we will do is we will just look at one more learning rule which is remaining, and then we will just look at all the learning rules together, just summarize them, and then we'll talk about multi-class perceptron classification. So the next learning rule that we have is Outstar learning rule. Now this Outstar learning rule is also a learning rule where we talk about a layer of neurons rather than a single neuron. Okay. And what we do in case of Outstar learning rule is it is used in conjunction with some other learning rule. That is I mean, it is not used directly on its own, but along with some other learning rule, that is winner takes all learning rule in a layered network. Okay. So what happens in case of Outstar learning rule is the weight update that is happening, it is happening for the fan out weights from a given input feature. So a given input feature that you have here is the weights which are fanning out from that input feature. Whichever weights are fanning out from that input feature, they are updated. Usually when we talk about updating weights, we talk about the weights which are coming into a neuron. Okay? But here, the weights which are fanning out from a particular input, only those weights are updated. Okay. And the weight adjustment is beta times d minus wj. Okay. Now this d indicates that you have a labeled data, so it is the kind of environment that it is used in is supervised. It's a supervised environment. D is the desired output. Okay. So each of these neurons will have a desired output, and on that basis, that the difference between that desired output and that weight is computed. Okay. This is the individual weight adjustment. It is supervised learning. And where it is used is, it is not used alone, it is used in some layered networks, like for example this counter propagation network. Now counter propagation network is a special network actually, which comprises of two feed forward layers. The first one is winner takes all and the second one is the outstar layer. So there are two layers. This is one layer and before this there is one more layer. Okay. So it is somewhat like this. You have the winner takes all here, and these are the neurons. Okay, for the first feed forward layer that you have is the winner takes all. So this is some Z input pattern. Okay, and then this one is a hidden layer. Now what happens is, since this is a winner takes all layer, what do you do in case of winner takes all? This particular layer actually is going to find out the winner. This is the cluster layer. This is the cluster layer, and this is the output layer. That is how you have it. Okay. Now, what is the application of these counter propagation networks? It is actually used for some mapping from some input to output. So y is equal to f of x, kind of a mapping you want to approximate, you can do it using counter propagation network. Or if you want to go for some kind of a compression, you can go for counter propagation network. So these are applications. But what happens here is, first, what happens, there are two stages of training this particular network. Okay. First stage of training is you use the winner takes all learning and you find out the winners and you update the weights of the winners. Winner takes all will progress in that unsupervised fashion. Okay, that is the first phase. And the second phase, what happens is you again out of these, you give the input patterns, and then what you do is you find from that winner, whoever is the winner, you update the fan out weights of that winner. Okay. And there are different variations of counter propagation networks. I'm not going much into detail because we don't have it as part of our syllabus. But only thing is, this is one more rule which can be used as part of a layered network. That is what you need to know. Okay. And how is it different from the other learning rules is that in this case, the fan out weights are updated and it is supervised. So you can see D is used here, the desired label is used. So in case of counter propagation networks, it's a hybrid kind of a learning which is happening. In one phase, there is unsupervised learning, which is typical in a winner takes all learning environment. And in the second phase, what happens is you have a supervised environment coming into picture because you are making use of that label D. Okay. So if you want to read more about counter propagation networks, I'll give you links for that. Just go through it if you're interested. But as part of the syllabus, it is not there. Just an application, I've just listed it here. Okay. So we will look at the learning rules that we have studied as part of the course. So these were the learning rules that we have looked at: the Hebbian, perceptron, delta learning, Woodrow-Hoff, correlation, winner takes all, and Outstar. So this is a short summary of all learning rules on different parameters, based on different parameters. So what is the single weight adjustment? What are the kind of initial weights that are required? Okay, we didn't talk much about this aspect, but of course, weight adjustment, everyone should remember the weight update equation, right? Delta W. What is delta W for each learning rule? You can never forget. So this table will give you a gist of all the learning rules that we have studied so far. Okay. So what is the type of learning? What are the activation functions which are used? Whether it is working on a layer of neurons or it is a single neuron. So we know that all the learning rules work on a neuron, single neuron, except for the last two, that is winner takes all and Outstar. Okay. So one short view of all the learning rules, if you want to have, you can look at this slide. So we are done with all the learning rules so far. And what we need to do now is we need to go ahead and we need to build networks now out of this. Just looked at learning rules from the point of view of solving very simple examples. Now we will slowly move ahead with developing layered networks. Okay. So the next topic that we have is multiclass perceptron classification. Now, there are some assumptions that we need to make here. The patterns that, the type of patterns that we need to classify, these are linearly separable. That is the first assumption. Okay. And the second assumption is that the pattern is belonging to multiple classes. So it is more than two classes rather. Okay. So if we want to actually design a network for this particular problem, assuming that the patterns are linearly separable and they belong to more than two classes, okay, using a perceptron. Now you just extend the idea from a single perceptron to multiple perceptrons. Okay. So how do we proceed? How do we apply this perceptron learning to a layer of neurons? Okay. So for that, just we'll solve this problem. Okay. And the same problem, in fact, I'll give you one more problem which is there that you can solve as part of the practical. This particular problem has three classes which are mentioned. So what are the classes actually? Classes are nothing but the number of neurons that you will have in the layer. So if you have n number of classes, you'll have n neurons, right? So you have three classes, okay? And these are three patterns. So first pattern belongs to class 1, second pattern belongs to class 2, third pattern belongs to class 3. Okay. And you have these weight vectors. So since we are having three classes, let us first actually visualize the network that we have. So there are three classes. That means you will have three neurons. Class 1, class 2, class 3. Okay. And you look at each of the patterns. So each of the pattern has two features. These are the patterns, x1, x2, x3, right? So has two features. Okay, so this is the kind of the network that we have. We are assuming that we are going to solve this problem by using a layer of perceptrons, a single layer of perceptrons. assuming that it is linearly separate. Okay. Now, what are these weight vectors that you see? These are weight vectors. Okay. Why there are 3 weight vectors given to you? Usually when we solve a problem, there is one initial weight vector. Why there are 3 weight vectors that are given to you?
3 neurons. So
Yes. So there are 3 neurons. So that is why you have 3 weight vectors. So W11 means that it is a weight vector uh, which is connecting to the first neuron. Okay. W21 means it is connecting to the second neuron. This one indicates it is the initial weight vector, W1, that we have. Then the next step you will get W2, right? That is how it progresses, W3, W4. W11 means it is the first neuron's weight vector. W21 means it is the second neuron's weight vector, and so on. Okay. One more thing that you will notice here is, since there are the input patterns are two-dimensional, I expect the weight vectors also to have 2 dimensions. Why there are 3 dimensions in the weight vectors?
three
Because of three
classes.
classes.
No. What are the weight vectors? See, what are the weight vectors? So when I talk about W11, I said it is the weights which are connecting to the first neuron, right? Okay. That means this will be the first one, 1. This will be -2. Okay. What about this third weight?
Bias.
Exactly. So this is a perceptron. Don't forget, whenever you're using perceptron or delta learning rule, which is continuous perceptron, you have to add the bias. Okay. Input patterns will be one dimension less. You have to add that bias. So you have to add an additional input, the bias input. This is x1, x2, and this is the bias input. Right. So these are the weights. 0, this weight 0, this weight value 0 is the weight connecting the bias to this particular neuron. Okay. So this is how your network looks like. So you just have to add one additional input and then proceed with solving the problem. So we will solve this problem for one iteration. Okay. So first, the hint is you create the augmented input vectors. Okay. Now you can use either -1 or +1 as a fixed input. If it is not mentioned, you can use any one. Either use -1 or +1. Okay. But here I am using -1. Okay. And assume that you're using bipolar binary. You know which activation functions you can go for when you're using perceptron? Either unipolar or bipolar binary. They have to be binary. That is important. It's a perceptron. Right? It's a discrete perceptron. When we say perceptron, it is a discrete perceptron. So either bipolar or unipolar, but binary functions. Okay. So if I assume it is bipolar binary, okay, what do I need to do? I need to have the output label in such a way that whatever outputs that I am having, they are either +1 or -1. The output of the neuron will be +1 or -1, and the labels also will be +1 or -1. Okay. But now, how do I characterize this network now? Okay. That means what is missing here is the label also is not given here. Only thing is it is given in the sense that pattern X1 belongs to class 1, pattern X2 belongs to class 2, and pattern X3 belongs to class 3. Okay. But labeling I have to do. I have to represent what is class 1. I have to say which vector out of, so I'll have to have a vector, right? There'll be a vector here. This will be a vector. Output vector. There's an input vector now. Input vector is always there. Input vector is a pattern. Output, usually you have, when you have a single neuron, you are looking at only this part of the network. Say this neuron, right? So usually have one output, but now you'll have n number of outputs depending on how many classes you have. Okay? So instead of a single output, now I will have an output vector. Okay? So what I need to do is I need to just encode these classes in the form of vector. So class 1 will be, since I'm using bipolar, so what will be class 1? It will be 1 minus 1 minus 1. Class 2 will be minus 1 1 minus 1. Are you getting it? Class 3, this is class 1. This is the output vector for class 1. Okay. Class 2, it will be this. Class 3, it will be this. Okay. Minus 1 minus 1 1.
मैम 2 को माइनस रखना है, ये जरूरी है क्या?
The higher the activation, it will be 1 0 0 or नहीं, उल्टा भी कर सकते हो आप. You want to say that if this is this is minus 1 and this is plus 1 plus 1, that is what you want to say, na?
Yes ma'am.
You can do it.
Okay.
Okay, but usually the ways we do it is it as 1 0 0, na? So that is what I used. Only thing is you have to ensure that the classes are uniquely represented by the vectors. That is what you have to ensure. Okay. So now with this, now problem is well formulated. Now we can solve it. Okay. So these are the patterns. I've just put them down in the table. Now what we have to do is weight vectors also given. Bias I have assumed as -1. Fixed input I have assumed in this problem as -1. Usually all the biases that I considered earlier were +1. Here let us for this example take bias as -1. Okay. So what is the next step? It's the same steps that you have followed for solving single perceptrons, but now it is a layer of perceptrons. Okay. So what is the next step now? Compute the net values. Compute the net values for each of the perceptron. Net 1, net 2, and net 3. There are three neurons, right? So compute net 1, compute net 2, compute net 3. So tell me the values.
8 0 15.
You use this only, whatever I have written here. 10 minus 4, 10 minus 4,
6
6.
0.
6. Okay, this is 0, minus 2, minus 2, minus 4. This is minus 4, hai na ye? This is minus 4.
Yes ma'am.
Last one is 17 or 16. What is it? 1 plus 6, 16, 17. 17, right? Okay. Now what you're doing is assuming C is equal to 1. Since we are using bipolar binary, okay, output will be either a +1 or a -1. Okay. So what is the output in this case? Just thresholding, right? If it is greater than or equal to 0, it is +1. Greater than, right? This is the output. And I'm assuming that I have used this as 1 minus 1 minus 1. Minus 1, 1, minus 1. And minus 1, minus 1, 1. Okay. So now this D is there with us, O is there with us. Should I use delta W everywhere? No. I will just look at where it is mismatching. Only those weights I need to update, because rest of the cases, delta W is going to be 0. If the outputs match, if D matches O, D minus O becomes 0. So delta W is 0. So you don't need to compute that. Okay. So which is that case? It is only this case. right? Because the outputs are mismatching. So what you do is you update the weights. Okay? So you come to delta W. What is delta W? Minus 2cx. Okay, so it's simply minus 2 times x. That is delta W. So what is it? 10 times minus 2. It is sine of d. Plus or minus, how do you decide? By d, right? Yes or no? Or you can use a normal rule, c into d minus o into x. Still you will get the same answer. This is just a shorthand equation for the same. So minus 2 times 10. So that is minus 20 minus 4, and this will be plus 2. Right? So these are the delta W values. Now using these values, we will compute the new weights. What about W1 and W2? What will be the weights? They'll remain unchanged because delta W is 0 in that case, right? So these weights we'll write as they are. Okay, only weights that we need to update are W3. So W3 is equal to the old W3 plus delta W3, right? So 1 minus 20, that is minus 90. 3 minus 4, that is minus 1. Minus 1 plus 2, that is 1. Okay. So these are our new weights for the next step, where the next input pattern is presented. That is 2 minus 5 and minus 1 is the next input pattern. So now the same steps you have to follow. Tell me what are the values for net? What are the net values?
12, 3 minus 34.
12, 3 minus 30. Correct. So accordingly, the outputs. Okay. So now which weights you are going to update? W1. Because they are mismatching, these are not mismatching. W1 you're going to update. So W1, since this is a minus 1, this will be minus 2cx again, correct? So it is going to be minus 4, minus 2 into this vector, right? This vector. Minus 2 times this vector. So minus 4, 10, and 1, right? Minus 4, 10, and sorry, 2, correct? Minus 4, 10, and 2. Update the weights using delta W1. So W1 will be updated. W1 is equal to old W1 plus delta W1. Okay. So this is, what is this? Minus 3, minus 2, yeah, 8, 2. Okay. And the rest of the weights remain same because there is D is matching O. Okay. Now the third input pattern comes. This input pattern has come. What you need to do is again find the net values. What are the net values? Multiply and tell me what are the net values.
23 -7
फाइव
माइनस
एट जा तो 40 हो रहा है, 5 8 जा 40, 15 45, राइट,
अच्छा सॉरी
55,
माइनस, हाँ
55 - 2 है ना, 53, 53 -5 -2 -7 and 95 90 -1 89, right, 18. So accordingly the output f of net will be 1 -1 1, right, and so what happens is, which weights are wrong? Again W1 is wrongly predicted. Okay, so you update the weights of W1 minus 2cx again. So minus 2 times. You're understanding now why it is minus 2cx, because D is negative. Okay. So minus 2 times x. So that is 10 minus 10 and 2. Right. So problem is not done yet. I mean, iteration is not complete yet. What you need to do is find the final weight. This is only delta W2. So don't stop here. Delta W1. Don't stop here. Final weights will be after this, one more row added. Okay. So I'll just write them here. What you have to do is you have to add this to this. Okay. So W1, W2 and W3 remain the same. So these are the final weights for W2 and W3, but W1 has changed. So we'll just write W1 here. So W1 is 7, right? Minus 3 plus 10, 7. 8 minus 10 minus 2. 2 plus 2, that is 4. So these two and this is W1. These are the final weights. Okay. So this is one iteration. So you can just, if you run this in a loop, you can go for n number of iterations. You can stop solving the problem by computing the cycle error. When it becomes 0, you can stop. Okay. So this is how the perceptron, single perceptron is extended to a layer of perceptrons. Okay. This particular problem that is given here, so there are 4 classes, and for each class there are two patterns which belong to that class. Okay, so what you need to do is these you have to apply this multi-category perceptron, multiple categories, right, perceptron learning rule, and solve this problem. So this particular problem you can do as part of the experiment. Okay? The next experiment. um, so I'm leaving this problem for that experiment. You can see, you can solve it and see, or you can do it for that experiment, because it will take a while to solve this. Next is the same concept. That means the network structure is the same. You have a single layer of neurons, but the type of neurons that we have are now continuous perceptrons. Okay, so if you're going to use delta learning rule for a single neuron, then you can classify the data into two categories. Okay, because a single neuron can give you two classes, but for multi-category classification you can extend it, so you require this as a layer of neurons. Okay, so this networks, what you have done is you just have replaced that the binary perceptron with this continuous perceptron. Okay, the symbol, you can see the symbol has changed to a triangle, this which indicates that it is continuous. Rest of the notations are similar. Only thing is now, I mean, you will have some additional inputs are there here. So it becomes a weight matrix. So Whatever you saw earlier is the same thing. Those vectors together form the weight matrix, right? So it's a matrix of vectors. So each of these is actually, each of these rows, each of the rows are the weights which are going from all the inputs to a particular neuron. Okay, so that is how you represent it. This is just a representation. Row wise, it is these vectors which are there. Okay, and so only thing is a notation here is the reverse. So what happens here in this case, what is done is, see, weight kj connects the output of the jth node with the input to the kth node. So what is the meaning of this? Notation is reversed. WKJ, this particular notation is, this is there in your textbook Zurada, is used. You can refer to that. Okay. So what, just, it's just a notation. So I'm saying that this a single weight is represented by WKJ, where K is the neuron number and J is the input which is being connected to that neuron. Are you getting it? Okay. Neuron number first, then the input number, input feature. Neuron number followed by input feature. Okay. So that is what. So this row, if I'm looking at this matrix row wise, so what is the meaning of each row? Each row represents all the weights which are connecting to a given neuron. Right? Yes or no? It is neuron wise. Each row is a neuron, a weight vector for a given neuron. So this is the weight vector for first neuron, O1. This is the weight vector for O2. Are you getting it? And so on. So this weight matrix is K cross J. Now, what you have is the same delta learning rule. You are extending it to a layer. So you have to use the same equations for updating. Similar to discrete perceptron, you are using the same equations, but now you have to use the continuous perceptron equations, right? So eta times, if you recollect, the delta W equation for continuous perceptron network, single neuron network is eta times delta times y, where delta is the learning signal. Okay. So if you recollect, we had derived this for the unipolar continuous neuron. It is O times 1 minus O. Do you recollect? Because O times 1 minus O is a derivative of f dash net. This delta that was there, the learning signal R, in fact, is delta. Okay. What was it in case of delta learning rule? It was D minus O times f dash net, right? And f dash net was O1 minus O for unipolar continuous, and half 1 minus O square for bipolar continuous, right? So the same thing is written, same idea is extended now to a layer of such multiple such neurons. Each neuron is a continuous neuron, perceptron, right? So for each of the neurons, you have to apply this weight update. Eta times, depending on either of these two activation functions, D minus O, either this part or this part you will use depending on whether the activation function was unipolar or bipolar continuous. Okay. And net, now you will have n number of net values. It will be a vector of net values. That is what we did, right, in the last table. A vector of net values we had. Right? There were 3 neurons. We had 3 net values. Okay. So this is a vector, okay, which will be obtained by multiplying the weight matrix W with the input vector Y. The input vector is y in this case. It is augmented. One additional bias is added. Okay. In case of both perceptron and delta learning rules, you have to have augmented input vectors, right? So this is nothing but MCPTA. This algorithm is MCPTA, multi-category continuous perceptron training algorithm. Okay. So the same concept you have to use. It is just given in the form of an algorithm here. Okay. So if you recollect, we had also discussed discrete the single continuous perceptron training algorithm SCPT earlier. So now that has been extended to the layer of neurons. Okay. So these are the steps that you follow. Similar steps. Only thing is now instead of a weight vector, you have a weight matrix. Okay. So that is what is given here. WK is WK plus half uh, DK minus OK, 1 minus OK square. K is the number of neurons. K is the number of neurons, as you saw in the network earlier. K is the number of neurons in that layer. Okay. So WK is the kth row of W, of matrix W. Each row in the matrix is representing the weights which are connecting to a given neuron. So you update the weights for all the neurons. That is what you do. You update all the weight vectors. That is what we did. If you recollect, we just solved that problem, this problem, right? What did we do here? We just updated the weights, right? One by one, weight vectors. W1 represents the weight vector which is connecting to the first neuron. W2 represents the weight vector which is connecting to the second neuron. So it's a weight matrix. This entire thing is a matrix, right? Where each row represents the weights which are connecting to a given neuron, right? The same concept. Only thing is that you're using inside the neurons that you're using inside are continuous perceptrons. Okay? So you have to use a delta learning rule. You cannot use the normal perceptron learning rule. You have to use the delta learning. Okay? And this is about the cycle error. Now in this case, only thing difference here between MCPTA and the discrete multi-category discrete perceptron training algorithm is the cycle error will never become zero here, right? Because the type of output that is obtained will be a continuous value. Okay. So it will be a value which is close to zero. It will keep on reducing. Okay. So you have to stop, you have to decide your threshold, Emax. Here. Decide it beforehand and continue. Okay. Rest all the steps remain the same. Okay. So what we have done is from a single neuron network, now we have created a layered neuron network, but it's still a single layer of neurons. Okay. Now this concept, we are going to extend it further where we have more than one layers of neurons. So we will add one more layer in between, which is nothing but a hidden layer. The same concept, we are going to extend it. And we cannot directly actually apply this rule. I mean, extend this rule very easily. We have to do some mathematical calculations there. Okay, and see how it gets extended to one more layer of neurons and many such. It can be extended later on. So we will actually look at what is known as the generalized, we have seen the delta learning rule. We will look at generalized delta learning rule. And from generalized delta learning rule, we will talk about backpropagation. Okay. So in the next lecture, we will be looking at the derivation of generalized delta learning rule, as well as how do we achieve learning for a layered network where there are hidden layers. Okay, and why is that hidden layer required? Why do we require that hidden layer? Because the kind of patterns that we are trying to solve, the problems that we are trying to solve, those problems are not linearly separable. Okay, so when the patterns are not linearly separable, then you need a multi-layered network. multi-layered perceptron network. Okay. And the learning rule that you are going to use will be delta learning rule. You are not going to go for discrete perceptrons. You will see that in all the libraries that you have available, you will have only continuous perceptrons which are available. So multi-layered perceptron, a perceptron, the discrete perceptron is no longer used. The continuous perceptron is used, and you're going to use the backpropagation training algorithm for training it. Okay. So we will stop here for today, and we'll continue with this in the next lecture. Thank you.